Welcome to Shuttlegirl.
Shuttlegirl is a pathfinding application for the Harvard campus. Instead of just checking the shuttle schedule, it tells you the best way to get from one building on Harvard's campus to another.
It takes into account your walking speed, preference for taking the shuttle or walking, and even tells you what the weather is where you are, so you can remember to take an umbrella or wear a jacket.
For our demo, we'll be starting at Mather House and ending at Memorial Hall. We start by entering the locations of our start and our destination. Then we input our walking speed, 20 minutes per kilometer, about 2 miles per hour. Then we enter 1 for no preference and hit submit. Shuttlegirl will assume you are leaving immediately if you leave the time blank as we just did. As you can see, Shuttlegirl's directions include both a shuttle ride from Mather to Boylston and walking from Boylston Gate to Memorial Hall, going by Memorial Church. But if we go back and change the settings, we may get a different result. Let's make ourselves half as fast as before and give ourselves a relatively high preference for taking the shuttle and see what happens. Now Shuttlegirl is recommending that we take the shuttle from Mather, but this time stay on it all the way up to the quad, then back down to Memorial Hall. So how does it work?
Given the source node or starting point in the graph, use Dijkstra's algorithm to find the shortest path between that node and the target node. The nodes of the graph represent Harvard buildings, and edges represent weighted distances between pairs of buildings and shuttle stops.
We have several implementations using different data structures for the graph, priority queue, dictionary, and set. Part of our goal was to find the most efficient combination of implementations to give our algorithm the fastest possible execution time.
We represent the graph with both adjacency lists and an adjacency matrix. For our priority queue, we implemented list, binary tree, binary heap, d-array, and Fibonacci queues.
A d-array heap is the basis for our d-array queue using Dijkstra's algorithm. The structure of a d-array heap is dependent on the arbitrary number d. We use d equals 4 in our testing. For example, a binary heap is a d-array heap where d equals 2. We chose to implement the d-array heap because it is supposed to be asymptotically faster than a binary heap.
The Fibonacci heap was too difficult for us to implement on our own in a limited time frame. However, we were able to integrate a pre-existing library into our code. We were then able to use it for comparison with our other queue implementations.
When testing our combination of priority queues, graphs, and sets, we kept track of how long each took to execute. We ran each variant over 100 times and compiled that data and used it to evaluate which implementations are the most efficient. For our graph implementations, the adjacency list was 8% faster than the adjacency matrix. This is a consequence of the low density of the graph. Our priority queue implementation were a little more surprising. We expected Fibonacci and d-array queues to be the fastest. However, there was no significant difference between binary tree queue and d-array queue, and the Fibonacci queue was much slower. We believe that this is because our dataset is relatively small, too small for us to see the asymptotic difference between the implementations. With a larger dataset, we expect binary tree queues to be slower than both the Fibonacci and d-array queues, not faster. Our results for the dictionary implementations met our expectations. The hash table implementation was faster than binary tree and much faster than association list.
In conclusion, Shuttlegirl works to find the optimal path from point to point, takes your preferences into account, and reminds you of the current weather. We also explored and evaluated many different data structures and implementations to choose the most efficient ones for our project.
Thanks for watching!